going through, you really have to kind of decide what it is that you want your students to come out with. I do quite a bit of CNC coding with my kids, and I do quite a bit of CAM. I go fairly deep into CAM with them, trying to teach them as many of the tips and tricks as I can, because I'm really trying to push more of my students to go into manufacturing engineering. I don't have very many yet, but I'm trying to get them to the point where they can see that they can be really comfortable with it, and they can see that there's such a huge need right now for people to be able to make molds and dies, those types of things. So I try to really get exploratory with them, and here for this first year, for the most part, you're going to want to kind of keep it fairly simple. If you have robotics teams, if you do the first robotics and that kind of stuff, and you're wanting to use your CNC machines, you're probably going to have to take it a little bit step farther, start trying to learn. Our team this year wants to start cutting their own sprockets and gears and that kind of stuff. So you're going to want to try to take it in your room that best is going to meet the needs of your students. You can go through the majority of this PowerPoint on your own. I don't want to waste a lot of time, waste your time. I just want to kind of focus on most of the basic codes. If you look at this slide here, for the most part, what you're looking at in black is the majority of the code that you kind of want the kids to memorize. They won't have it memorized right off the bat. The more they do of it, they'll just start to kind of get it. But knowing the difference between absolute and relative codes, it's becoming a little bit archaic. In near as much relative coordinate systems as you used to, but they still really need to kind of know the concept of it. They're really, when they start hopping into EdgeCam, some of the dimensions and some of the numbers that EdgeCam are getting are relative to where it is. Some of them are absolute. So being able to bounce back and forth, trying to teach them a little bit of Cartesian coordinate system is almost a must. So go through with them absolute and relative, and for those that don't know and aren't as comfortable with absolute and relative, we'll kind of do that here in just a moment. Being able to do non-cutting movements, straight line movements, and then clockwise and counterclockwise. Those are the main prep codes that you kind of would like for your students to know. Just as a reminder, has anybody gotten into G&M codes yet?
Yes, we are. This is Glenn.
Okay. Anyone else?
No.
Yeah.
No.
I did. Ali.
Okay, Ali, so you have and Glenn has.
Yeah,
So,
I did the but I'm almost done with them.
good. So for the most part, you're going to have to kind of teach them a little bit of tricks, how to kind of memorize the difference between G02s and G03s, and I can give you a little hints here in a few minutes. But for the most part, your G codes are going to be your movements. And then M code-wise, your same thing, it's pretty much the ones that are in black here. How to end a program, turn the spindle on, turn the spindle off, tool changes, those types of things. And you'll have smart kids that will ask little simple questions like, okay, so I see M01, M02, M03, what happened to M04? And, it all has to do with your experience and practice and those kinds of things. There is such a thing as an M04. So really what should happen is when we make this PowerPoint, that is a spindle on, it just happens to be spindle on clockwise. And then the kids can kind of get the gist that M04 must be spindle on counterclockwise. It's just something we don't do. So there is tons of code that we're not teaching the kids. They can kind of see all of a sudden that it's going to hop to an M47. Yeah, that should give them the gist that there's all the way from M11 up to 47 and then. So there's tons of code that we're not going to be teaching, and some of it's machine specific, and some of it just doesn't relate to the Intellitech equipment. Like Chris was talking about last week, the Intellitech equipment is so nice that it's kid-friendly, that your kids can be fairly productive by only knowing a small amount of code. So by no means are you trying to teach your kids how to be proficient at writing canned cycles and great big pockets and those kinds of things. You're just trying to teach them a little bit about being able to read code. So just don't give them the expectations that when they're done with this, that they're going to be going out writing codes for some big fancy things. That's what EdgeCam is for. So code-wise, your M codes and your G codes are going to be the major things that we want to be able to do. And being able to know the difference between your arcs. I don't know about Chris. I don't have my students write relative arcs at all.
Nope.
So whether they're in radiuses or whether they're through center points, I just don't. So when you look at the activities themselves, what we're asking the kids to actually do is we're asking them to write their initials in absolute and write their initials in relative. So I'll open up the absolute for those that haven't been able to get this far yet. There's a little example that kind of comes up here on the front, and that's the idea. You're going to use Ren shape, you're going to use MDF, you're going to use wax, you're going to use whatever you have, and you're giving them a 2x3 envelope that they're trying to create their shapes in. So they have this little map that they'll be able to draw directly on. What you see right there is what I have my students do. I give them little circle templates, and they draw little circles where each one of their points are going to stop. I have them draw the tool path with some dotted lines. I have them draw the outside of the tool paths with a little bit of offsets. I want them to look as realistic on the paper as they're going to be in real life, because kids have a hard time understanding that every time the bit stops, it's leaving round things in different places, and they don't pre-plan for some of that. So really having them do some cool sketches, give them colored pencils. You know, they go home and, you know, hey, what'd you do at school today? And we colored. Yeah. So what did you color? Oh, we colored coding. Okay, so that's a little bit better. So I make my kids have at least 3 arcs somewhere in their program, and then you'll have kids come up and be like, well, I have all L's in my name. I have no arcs. Well, then you're going to have to be a little bit creative about it and figure out how to put an arc into an L. Or you're going to have to make me some kind of fancy shape instead of your middle name. I don't know. But I require them to have 3 arcs. So they'll go through and they'll find every single one of those points, and they've got their little map that you can print out and hand them, and then they'll start writing their points and then start trying to turn that into code. I don't give them this sheet anymore. Majority of my students got more confused by this sheet than they did anything else. So most of mine just sits either in Notepad, Google Doc, Word, and they sit there and they type it. This just became a little bit too much if they were trying to remember which boxes they're supposed to have. Chris, do you still use this sheet?
We do not. I do the same thing too. I have the kids either start writing it on this piece of paper, on a blank sheet of paper in their notebook, or in Notepad or Word, just so that they're not, because their big question is, how come there are so many blanks on every line of code? Well, not every line of code requires that. So if you use this, just be prepared for those questions and say, look, you know, not every line of code has to have every box filled in. Eventually the kids will get it, but I've found, and I think Jim too, if you give them a piece of paper and say, just write down the codes you need, and if you look at this PowerPoint, the PowerPoint that goes along with this, it's awesome. It tells you your first line of code should do this, your second line of code should do this, and it tells you step by step, and the kids then have to look at the PowerPoint and translate what line of code, the G90, G20, every time you write a program, those 2 lines of code should go first in my classroom. Then you do a tool change. Well, Jimmy just used the machine. He did the same program, and he's using tool 1 too, so I don't need to do a tool change. And I tell him, no, that's wrong. You need to put a tool change in, because what if Jimmy didn't use tool 1? Or what if Jimmy changed the tool, or you put the wrong tool in the machine? You want it to do a tool change first so that you can check it, and so on and so forth. And so it's a great way to say, once they've written it a couple times, they figure it out, and they say, hey, you know what? Can I just take lines N1 through N6 and replace the X, Y, Z values with the values from my program and just use that over and over and over again, just copy and paste? Of course you can. That's the idea. So then they just go and they put in all their points. So to answer your question, Jim, no, we don't use that sheet anymore. And the kids, I think, are good with it.
Even when you get into much more complicated code, entrance codes are entrance codes. So kind of compare it to your kids like writing a paragraph or writing a paper. So they're going to have their introduction paragraph, It's going to be explaining what they're going to be doing in the paper. It's going to be trying to lay out what their hypothesis is, and all that's all of this stuff. So if we look at this, and I make my kids comment every single line when they're doing their program. So being able to look at it, these first two lines, we're telling them that every point from here on out is going to fall into an absolute coordinate system. Every point from here on out is going to be measured in some kind of inch system. Those are, you'll see in the PowerPoint and in the documents, those are modal codes, M-O-D-A-L. Those are codes that once I've established them, I don't have to say them again. You'd like to think that that's like expectations in the classroom. You know, you come in, you read the board, you sit down. This one actually does what it's supposed to, not like my students, so I don't have to say this over and over. I can say G20, G90, and the software actually does what I ask it to. Tool change, like Chris said, it's not essential that it's there, but the nice part about it is I know every time their program gets ran, I know how the machine's going to react. And the very first thing it's going to do, it's going to retract all the way up to the top. Once it's up to the top, it's going to pause there, and it's going to allow me to start running from there. So I'm not going to hit start and hit run, and all of a sudden it's going to react in some kind of way that I don't anticipate. It's going to stop everything, it's going to run up to the top, and it's going to sit there and wait for me to come over and tell it to go from there. Be careful about this spindle. If they don't actually simulate it in the software and they just do a verify, the verify can't tell you that the spindle never turned on. The verify will look nice, you got this little red cube, it's pretty, and they'll never turn the spindle on. If you use the simulation in CNC Motion, it'll actually come down to the material and it'll tell you that an impact has occurred. So there's little things that is a big difference between actually knowing how to use the simulation component of CNC Motion rather than just that little red verify. That's the bad part, like the Tormach and some of the others. They have a little verify to them too, but it's just very simplistic. It won't go through and check spindles. It won't check feed rates. It just doesn't. So this entrance code up here, the basically line 1 through 6, for the most part, that's the same for every one of my kids. The only thing that I change when I type this PowerPoint in my classroom, I don't like a clearance of 0.1. 0.1 for me, it's a little too close to the part, and when you're coming straight down to the part and then getting ready to plunge into it, I don't have a big reaction time for 0.1 down to the material. So I change that 100,000ths of an inch to 0.25.
All you need to do is drink more coffee.
That's just my personal preference. Anytime. Yes, and I can act faster. But my kids still don't act faster. When they're doing the initials, I don't go deeper than a 1/16 of an inch. That way, if there is an accident and they screw up, I just face the top of the part off and we do it again. There's no point in really going that much deeper into the material. We're just trying to cut it in. So that part up there, N1 through N6, that's really going to be the same for every single one of their programs, except for this X and Y. This is going to be going over to point A. Kids will ask you simple questions like, can I swap 4 and 5? Some people will tell you yes. Most people will tell you no. Up in the measure, so tool change, it stopped the spindle, it went all the way up the top. The kids were like, well, it's going over to the position all the way up in the air. How do I know if it went there? Yes, that's partially true, but you always want it to go to it and then down to it rather than down to it and then over to it. If you go down and over, there's chances that you'll run into the vise, you'll run into clamps, you'll run into bolts that are holding things into the place. So there is a rhyme or reason to the order or the sequence that you're trying to tell them to put things in. It's not just, well, I could swap 4 and 5 and it wouldn't change anything. It might not change anything. There's a good opportunity that it could and accidentally run into something. So before we get into 7, 8, 9, 10, we look at this part here, and this is where we want to quickly discuss the difference between absolute and relative. You will have some kids that just cannot wrap their head very well around relative. It's a foreign concept to them. The absolute is what they typically do in their math classes. Origin is 0, 0, A is over 2/4, over and up 2/4. So we're going up 2 squares, down 2 squares. That's half inch, half inch. The kids get this one. They really don't have a trouble, or they really don't have a problem understanding absolute coordinates. So grabbing that and reproducing it, I show them this. I print this slide out and I hand it to all the kids. And then as we start doing this, I don't show them this entire program all at one time. They help me write this program pretty much directly onto the screen, just using these coordinates. So I kind of poke and I prod. I'm like, okay, so I want this, and they're looking at their list that you can get from the curriculum that tells them all the different codes, which looks like this G&M code reference sheet. It has all the codes that they're going to need, the same sheet they're going to get on the final. I have them use that with this, and I leave these out, these coordinates. I blank them all out, and they help me get all these coordinates together. So we use these 3 slides kind of as our springboard to being able to do it. Just throwing a slide up doesn't do me a whole lot of good, not with the kids. So I kind of let them help me build the slide. It takes a little bit longer to be able to do it, but I think they get a little bit more out of it. And then once we have that, we jump into the incremental. So if you take a look at the incremental, I'd like for you on your own, just for a moment, try to take a look at those numbers and try to figure out what the heck is going on.
And notice also that letter A, the first place that you go on your part, make the first point that you go to, make it absolute. And then from that point on, make it relative. Don't try to do it relative from the tool change. Always start in absolute mode. Do 1 point in absolute, and then make it relative. For kids in 9th and 10th and 11th grade that are seeing this for the first time.
So hopefully the gist of what you've gotten is they're not really coordinates, they're measurements. So if I'm looking at B, B is comparative to A. A is now the origin. The origin is going to move. The origin is going to constantly be moving. Wherever I am, that's the origin. So they're not locations, they're dimensions. So I'm telling it not to move over on the X, and I'm telling it to go 1 inch up on the Y. I'm telling it to come down 3/8 or over 3/8 and down a half inch. So they kind of have to now really start getting that concept of positive is up this way and negative is down that. So they really have to kind of get that, oh, hey, finally something I can do with the math that I told myself I would never do anything with. No, that's algebra. I'll never do anything with algebra. This we'll actually use. So we go through, and it does the exact same thing. I typically have kids struggle with this more than the absolute. They get the absolute pretty decent. So what I would suggest is here in the next day or so, if you haven't had a chance to go through this, is really start to look through this code and try to interpret it. If you have questions on why was this code used here and so on, the spindle speeds, that is not necessarily calculated because they never told us what this thing was made out of. They didn't tell us what kind of tool we're using. They didn't tell us how many flutes it had. They didn't tell us it was a high-speed steel or carbide. We don't know any of that. These are just given numbers. It's also kind of funny, whoever made this slide, it's incorrect. I need to ask Gerald again, if this is a plunge rate of 9, this should be a feed rate of, anyone? 18.
18.
That's just the math of it. Feed rate for plunging is always 50% of whatever your other feed rate is. Either one. So if this is going to stay 16, then the other one should have been 9. So it's kind of funny. Whoever made this slide, that's one thing that needs to get corrected. I think they did it right. They did it right up here, but then it didn't. So my kids caught that again this year. Like, oh, that's not supposed to be 16. It's supposed to be 18. So ironically, I leave the error usually just to kind of see if they'll ever catch it, which most of the time they always do. But let me also do it here.
And if you go back one slide, Jim, to the beginning, the first slide there, notice too in the program that they have in the example program, you start in absolute mode and you do the tool change, turn the spindle on, go to point A, and it's all absolute so far. And as soon as you get to point A, you're up to 1/10 or 0.25 above point A, then you enter incremental mode and then go incremental from there. Otherwise, it gets really ugly because you have no idea really where the XYZ value of the tool change is. So that makes it a little bit easier for kids to understand too. Just don't forget that when you do your relative for the first time.
Should add G28 for that.
Yes. And some machines will understand that. Our IntelliTech machines will actually do G28s. That's one of the things that we talk about, that for the most part we cut out a lot of extra codes. So what he's talking about, the G28, is actually on your machine. You can teach it, this is a known point, wherever it is on your machine. You can say right here, this is 0, 0, 0, whatever. You can tell G28, and as soon as you do that, it will go to that known point, and you can start running incremental straight from there. For the most part, that becomes a little over the top for some kids, and they just get the gist of, hey, I can hop back and forth between relative and absolute as many times as I want. Well, yeah, you can. So we actually end the program that way too. We go back to a G90. We retract up to a safe position of Z2. Move the table to 4-3, and this may not work for you. That X4Y3, it has to do with where you put your vise on the machine. If your vise is way over onto one side, you might not have soft limits of being able to get to X4 and Y3. So some of these numbers, you have to kind of tweak a little bit more specific to your machine. But I can tell you the retract idea and the plunge idea, that's typically when kids go into their CNC motion. That's where they'll screw stuff up.
Yep. One, they'll put in...
what I want to do...
Go ahead, Jim. No, go ahead. What will usually happen in this is...
I'm opening this up.
All right. When they... the big thing, the kids have said this to me many times. I'll tell them to do a 16th, and they'll miss a decimal point. Instead of 0.125, they put in 0.25, and all of a sudden it's like, whoa, it's not supposed to go that deep. Yeah, it's only 1 decimal point, they'll say to me. Well, 1 decimal point is huge, especially when it's a tenth. So I usually have them go through in your software. If you notice, the software will print all the Z values in red so that you can quickly go through their code and check all the Z values and make sure that the cut increments are what they're supposed to be.
So my CNC Motion on this computer is expired. Next time I'll bring it up. What I want to show you next time, I want to show you in CNC Motion that little red verify. If you've ever been paying attention to it, that little red cube that you can make it run, it will do more than that. You can turn it into wireframe, and it'll actually show you every single one of the kids' rapid movements. It'll show you their G01 linear movements. You can turn it to the side, and it will show you every single one of their plunges and where they match up and in relative. Some kids will all of a sudden be able to see that they start going deeper and deeper and deeper and deeper into the part because they're not really doing relative. They're kind of, it's Spanglish to them. They're not typing in absolute or relative. They're bouncing back and forth and doing a little bit of both. So I told you a couple of little tricks that I teach the kids as far as memorizing. I go back up to it. And I don't teach any can cycles. Things like G02 and G03, trying to help the kids remember which one is which. I try to make it easy, and this one is clockwise. That's 2 things, and this one is counterclockwise. That's 3 things. I don't know a much easier way to remember it than that. G02 is clockwise, and G03 is counterclockwise. Dwells and pauses, you can talk to them about the difference. There was a question on the final a couple years ago that had to do with which one of these elements can be used for multiple things, and F can be used for time. So you kind of have to explain it to them a little bit, because there's some questions like that that kind of pop up every once in a while in the final. There is also a decent section at the end. What we really need to do is we need to expand this. We need to have a much bigger list of what the heck is wrong with this. And by the end of your first year, you probably could have a pretty decent list of what's wrong with these.
And next time when you take a look at, when we open up CNC Motion and you take a look, the kids will get the same errors all the time. Like if you're looking at this slide right here, look at any of these given lines. If you put a space, you talk about syntax and programming, if you put a space between the G and line N1, put a space between the G and the 0, or between the 0 and the 1, that's going to cause an error. If you put a space between the 1 and the G, there's no problem with that, but that right there is going to be an error. That's going to be an error. And if you put it in...
Same thing if they...
Go ahead.
Same thing if they put errors in here. Sometimes they'll be doing decimals and they'll do X space 0.2. CNC Motion will pop up and will say missing numbers. It doesn't... CNC machines don't actually read this like we do. If I was going to read this, well, first of all, I can't have a rapid and so let's go to a regular line of code. So like this line of code, I read this as linear movement on the Z in the negative direction, down 0.1625 at a feed rate of 9. CNC machines don't read code like that. For a CNC machine, that is one thing. So it actually doesn't even matter the order how some of these things are. I can put the feed rate in front of some of these things. It doesn't interpret it from left to right the way that we do. It's just code. So if they put spaces in places, as it reads it as one sentence, one word, it can't get it farther in the line of code, and we'll tell it, hey, I'm done. There's not enough parameters. There's not enough information for me here, and I can't do anything.
Hey,
the nice part about CNC Motion is every time it pops up with an error, as soon as,
I have CNC Motion. If you want me to pop it up, I can show a couple examples.
Sure.
Okay, let me, go ahead.
Let me change that over to you.
Yeah. There we go. Okay. So can everybody see my screen?
I can see it.
If you ever play with CNC Motion, the windows don't like to go back where they belong. So if you go to Window and say Run and Edit, after you resize your screen, it'll put everything back. And my kids are doing a project right now, and the project is a phone amplifier to play your phone. It's a passive amplifier. It's really pretty cool. I'll show you some pictures afterwards if you want to see them. But here's the code. And while Jim was talking about errors, I was actually putting errors into my code so that you could see what the kids are going to get. So for instance, Jim said there were 2 different buttons up here to watch your code run. The verify button, which is where my mouse is right now, and the run button. And if I try to run this, it tells me, well, the machine has to be homed first. We'll talk about that later. The only thing I want to talk about right now is we want to verify this code. We want to see if this code runs. Pretend this is your initials, or your kids are doing their initials. They can actually check and see if they've got the code correct. I took this first section of code here, and I actually put some errors into it so that you can see what a kid's going to do when they go to write this code. So they're going to go to verify. Verify the program. Yep. Let's invalid T code. What's that mean? What that means is that you called out a tool that doesn't exist in your tool library. So when you look at your tool library, I go to tool 17. Oh wait, there is no tool 17. So right away, the kid knows if he gets a T code error that this tool code is incorrect, and it's supposed to be tool number 7. Okay, so it was a typo. So let's try it now. We're going to verify again. Okay, we got to the tool change, and I tell the kids you have to look up top. You have to see what it's asking for. It's asking for your input. Insert tool 7 now. Press F5 to continue, or a green button. Oh, they're going to get this all the time. And the first thing they do when they get an error is close it. And you ask them, well, what error did you get? Oh, I don't know. Where was it? I don't know. Well, if you close this, you won't see where the error is. If you leave this open long enough, you see that it's on line N7, where my Z02, there's an error. Can anybody tell me what the error is? Can you see what it is? N16,
I can see
N7. I say okay, and I see that 0, it's a 0.
It's an O instead of a 0.
Correct. It's supposed to be a 0, but it was an O. You see how it turns red now? So that's a Z move. So let's try to verify again. Insert tool, go.
It'll also, as soon as they hit OK, it will be blinking exactly where it stopped in. Because remember, it reads it as one solid line.
Right.
So as soon as they hit OK to it, the cursor will be sitting there blinking right where the error is.
And so now there's an error on line N10, and it says missing numbers. And whenever you get a missing number error, you go to the line of code and you'll see that, okay, there's a space where there isn't supposed to be. So if I get rid of that space and I say verify now, let's see what happens. It'll go through. And if once I get the kids say, oh, I got an error at the end. No, that's the error message you're supposed to get. Normal program stop. So it's gone all the way through the program, and the program's actually worked. So those are the main things. Those are the main errors.
The best part is when they're doing relative. The best part is when they're doing relative, they'll run their program, nothing will happen, they'll see absolutely nothing, and they'll say, normal program stop. That's when you actually want them to go over to the simulate. They'll typically go to the simulate, and it'll be doing everything up in the air. The verify can't do that. The verify can't show you that because you can't see the tool. The tool just happens to be off the screen and nothing is happening. But in the simulation mode, you'll actually see that it never went down to the part because they probably, either with their G90 or G91, they didn't bring it down to the part first, and then they didn't retract or didn't plunge down into it at the right depth, and it's machining error. Hey, Chris, can you go over to your little verify window?
Yep.
And can you put it in wireframe?
If you tell me how.
Okay. Right next to the little red eraser, you have a little white eraser.
Little what?
You have, go over to your little verify window. The very top, it doesn't have to be verified. You've already got something verified. So just go to your verify window. In the top left corner,
gotcha.
You have a little eraser in your verify.
Gotcha. There you go.
So click on the other one. So as soon as you do that, the dotted lines will show you rapid movements. And all the other ones will show you things that are G01s. You can right-click anywhere on that view, and you can change the settings of that, and you can get the opportunity to choose the top or the front, and you'll be able to see the depth. So if he goes to setup, once he's in setup, if he goes to front and hits OK, then he'll be looking directly onto it from the side and be able to see every single one of those plunges, be able to see each one of the retracts and where the levels are. That's really helpful for me when I do relative. I make the kids turn that screen into me. And you'll actually be able to see that it starts walking down into the part, or they don't have, because it should be one solid blue line all the way across there.
This is also where if you need to change the size of your stock, if your stock is the wrong size, you can come into this window, click on stock, and type in the X and the Y and the Z coordinates, the X, Y, Z sizes of your stock as well.
So all in all, for what it is, CNC Motion is an extremely powerful software. It'll give them a decent preview of what it's going to look like. You as a teacher can pretty much scan their program pretty quickly looking at Z values. They can actually set up the machine. They can find the origins. They can teach the machine the origins. If they don't teach it right, it won't run right. There's all kinds of really cool things that you can have, all 10, 20, 30, 40, how many students you have, all at one time, being able to run this instead of going over and cramming them all into the mill at one time. The other part that Chris just did, if you open a program that has already been previously saved, it will come in locked, expecting that you might accidentally make a change to it. The kids will do the same thing. It'll have a gray screen, and they'll have to go down to the lock and unlock it.
Notice that now that I'm trying
Once
to
it's unlock it, have a bright white background.
and once you're trying to run it, you see how the screen turned gray? If I verify this, I take a look, and what I did was I took one of my old students' initials code, and they went a little crazy. They were the Bluebird. They went a little bit ahead. But you'll notice every single line of code is remarked. They went down through, and here's your exit code, and here's your entrance code. And then they even remarked every single letter. And what this did was they actually made a yo-yo that said CAS 2011 on it. That was the year that they did the yo-yo. But when that's gray, you can't click in here and edit. And the kids will do this all the time when they first open it for the first part of the day. You have to go to edit and unlock. Click on this to unlock it. It'll turn white, and then you can start editing it again. When you start do your code with your students, common errors that you might get, again, if you go to our website and you take a look under solutions, in solutions, like for instance, that the coming up gray and unlocked, I can't do anything with. It's in solutions under, sorry for the slow internet today, people. Must be that snowstorm. But anyway, when it does come up, there will be a solutions tab. You go to CNC solutions, CNC solutions, CNC motion solutions, and it'll say, what happens if I can't edit my code? It tells you how to change it. What are the steps to perform a simulation in CNC motion? If you want part of this to do over again, you can download the directions here. And there's all different kinds of solutions. You can take a look and see. Jim did that one. Where's my machine? Bad arc errors. If a student gets a bad arc error, what's the problem? How do I put new tools in? If I have a tool error, how do I fix that? My screen's locked. What do I do? Those are all the different, we took all different things that kids could possibly go wrong with and tried to make a solution for it. If you come up with other problems, let us know and we'll try to fix those too. But the difference between, we have, go ahead, Jim.
Like that bad arc one he was talking about, the bad arc one that he was talking about, you will have to teach the kids inside the machine. When we're writing arcs, I told you a minute ago, I don't have my kids write incremental arcs. In the real world, EdgeCam, MasterCam, SurfCam, all of them, they will do incremental arcs. Every arc they do is incremental arcs. I don't know why, but they do. You'll have to teach the software to interpret all the arcs as incremental. When they handwrite them, they have to interpret as absolute. So they'll get it and they'll write the whole thing up. And the kid the year before them left it on EdgeCam, and it'll say bad arcs, and they're like, oh, I did everything right. Yeah, maybe, doubt it, but maybe, and it will just change this little setting right here, and we'll run it, and oh, shaboopy, it's still a bad error. So,
and it's this one right here.
There's a little setting. Chris, can you run through real quick? Yeah, there you go.
Yeah. So here's, if you run a program, and in EdgeCam it requires one way, hand code the other. If this isn't checked and you get a bad arc, check it. Say, okay, try it. It'll probably work. Or vice versa. If it's checked, uncheck it. If you're going from hand code to EdgeCam or EdgeCam to back, either way, just flip that and see if that solves your problem. And I guess one other thing that I wanted to show you real quick before we get much further, I just got 37 updates to my LMSs. And one of the updates said that, hey, you have a new engineering formula sheet. And Jim was saying that the engineering formula sheet now has your G&M codes on it. So these are the G&M codes that they will expect your students to be able to use, and they're given to them on the formula sheet. So when you get your new formula sheet, you can take a look and see that. That's on page 5, bottom right-hand corner. And Megan, you'll be happy you've got your digital electronic stuff right on the same page with it. So the kids can be using the same page. Perfect.
Oh, yeah.
And yeah, it's all new. They've rearranged it a little bit. I've cut out, since I don't teach CEA, I can get rid of pages 6 and 7, both pages, aerospace too. But I have just a few minutes left. I wanted to show you one other thing in CNC Motion while we're here. The difference between verify and run. Run, this is a simulation software, and simulation allows you to pretend as if you're standing right in front of your $20,000 Super Pro Light 1000 without breaking any tools and without ruining an expensive piece of equipment. The only thing that's nice about the simulation is it works exactly as if you were standing next to the machine. So if I verify, I just want to check my code over here to see if my code is going to work. I can click that, verify, and it'll fly through and be done with it. Normal program stop, awesome. But now I'm ready to go run it on the machine. A couple things that you have to do when you actually run it on the milling machine is you have to home the machine. The machine has to know where its work envelope is in relationship to the XYZ axis. So you have to home the machine by clicking on this home button. And this is exactly what you'd have to do at the real milling machine. So the machine would then go up and over, and it would hit limit switches until it knew its limits on the X, Y, and Z axes. Once that was all done, you have to literally drive your tool to the front corner, or whatever you called your part reference 0. In this case, I made the front left corner part reference 0. So I would have to drive it, and there's a neat little feature in I can send my tool to a corner by clicking on that icon, and it doesn't work like that in the real milling machine. You have to actually physically drive it there. And once I'm there, I have to have the kids remember to go to Setup, 0 Position. Are you sure you want to make that 0, 0, 0 on all your axes? Yes, I do. So once I've done that, I can click the Run button and click Run Program. And it's not only going to verify, but it's going to simulate in real time. So whatever settings I've given this, the machine is going to run in real time, making that part.